Hey everybody, so we are going to try to start estimating means, which really just means we're going to use a sample statistic like X bar and use it to estimate a population parameter like mu. So using X bar to provide a plausible range of values for mu. And I'll just go through the four-step process on all the kind of the key things that we need to know to actually make these confidence intervals. Again, estimating means we're just going to use X bar to predict or provide a plausible range of values. We're using X bar to predict mu. So the first thing, of course, is state we're doing a one sample. We're only taking one sample, calculating an X bar, and we're going to create T intervals, not Z. So with proportions, we just use Z-scores and normal distributions. For means, we are actually going to use these things called T distributions, which are not very different, and I'll go into more detail here in just a second. So to create this interval, much like proportions, we're going to start off with our point estimate, our statistic X bar, and then add and subtract the margin of error. So the margin of error can definitely be expanded in this formula, and it's going to change a little bit because we're not using p hat anymore, we're using X bar. So the margin of error is the critical value, which again is not Z anymore. With means, the critical value is actually T star. And then the standard error for the sampling distribution of X bar is the sample standard deviation divided by the square root of n, which hopefully looks pretty familiar. And this really brings up why we need the T distribution. This sample standard deviation is going to have a lot more variance, a lot more variation than the population standard deviation. So to compensate for that, we are going to use this T distribution, which looks mostly normal, but again, it's more spread out. It compensates for the high error here. So here's a little visual depiction to hopefully help you out. Maybe a normal distribution looks like this. Very emphatic peak in the middle, really small area in these tails. So a T distribution, maybe it looks more like this. The peak's not so large, and again, there's more variance, more error in the tails. Now, as the sample size increases, we eventually become normal. In the T distribution, it's very flat for very small sample sizes. But enough of that. Let me just erase these. This is the formula that we're going to be using for the rest of this week and in the next. So we need to figure out how to get these values. How do we get that T value? So anyhow, before we actually do that, we need to move on to the plan step, where we check conditions. Conditions remain the same as we did with probability for the most part. The first condition, of course, is make sure the sample was selected randomly, just by reading the problem. The second condition is to make sure the shape is normal, or at least approximately normal. And there's a few different ways to do this. First thing is maybe the population is normal to begin with. If the population is normal and our sample size is small, our distribution should be normal. Another thing is the central limit theorem. As long as that's met, we can assume our distribution is normal. The central limit theorem, which, if you forgot, just means the sample size needs to be greater than or equal to 30. It's kind of a rough guideline. Now there's a new one that we need to check, and it's for really small samples. So I'll write it out. For small samples, those that are less than 30, the data of that small sample needs to be roughly symmetric with no outliers. No blatant, obvious outliers. Nothing that clearly doesn't belong. And again, if these conditions are met, we're not using a normal distribution. We are going to use a t distribution. We need a distribution with more error, especially if this was the only condition that was true. We had a really small sample size, but their data was roughly symmetric and didn't have any outliers. That sample standard deviation is going to be massive. The sample error is going to be massive. To compensate for that, we use a t distribution and not a normal distribution. But anyhow, the third condition to check, of course, just as a reminder, is the 10% rule. I always call it the 10% rule, but maybe in some statistics problems, you might also see this referred to as, also known as the independent rule. Observations need to be independent. That's just about it though. All right, so let's move on to the next step. As if we were actually building a confidence interval, the next thing would be let's actually do some calculations. So this and this, the next step again, actually do some calculations, create the interval. All we're going to focus on today is that t value, finding the critical t value. So what I need you to do in order to find the critical t value is just maybe do like a simple Google search or something, look up table B. Table B will literally give you the possible critical t values for all different sample sizes, confidence levels. So let's pretend, let's do like a quick example. We had a sample size that was 10. We had 10 observations in our sample, and we wanted to build a 95% confidence interval. One other thing we need for table B is something called degrees of freedom. Degrees of freedom is very easy to define. It is the number of observations minus 1. So in our case, since we had 10 observations, our sample size was 10, we're just taking 1 away. We have 9 degrees of freedom. With all this, we can absolutely get a critical value, critical t value. Again, just look up table B, open up probably the first link would be fine. And let me show you what it looks like. It's this thing. Table B shows you a t distribution and their critical values. Again, our situation, we had our degrees of freedom, and minus 1 was 9. And we wanted to build a 95% confidence interval. So that's this, was that the fourth column, I guess? So these two things intersect right here, which means we have a critical value of 2.262. And that's really all there is to it for using this, this table. Going back to our problem. The critical value, pretty sure I remember this correctly, it's 2.262. And again, that's all we're really focusing on today, finding critical values and checking conditions. There's that new condition for the normal step. If the sample size is small, it can still be okay as long as there's no clear, obvious outliers and the data looks roughly symmetric. All right, so let's try a few practice problems. The conclusion statement is pretty much the same as we were. You know, you say something along the lines of, we are 95% confident that the interval from this to this captures the true population mean. And then you just add some context. And we'll actually build the intervals in a later class period. So anyhow, like I said, let's go practice some problems. Go over here and here. Just make sure I clear everything. Okay, practice problems are right here. So this problem, finding critical t values, again, that's really the focus for today. It looks like this person took a random sample of 17 different trees, measured their heights and such, found some sample data. She wants to construct a t interval for the mean height of all the redwood trees in our park with 95% confidence. So again, you just got to be a little bit careful when you're using the T distribution table, table B. Even though the sample size is 17, we need to use 16 degrees of freedom, the sample size minus 1. And again, we're doing this for 95% confidence, 95% confidence level. So let's go to table B and figure out what this critical value is. 16 degrees of freedom, 95% confidence, so 2.120. That is the critical t-value we should use to create our interval. 2.120. And that's about it. We could try another one just for fun. Let me clear this stuff. What is the critical value, t, not z, for constructing a 99% confidence interval for a mean, and the sample size is 10. So again, the sample size is 10, but when we go to this table, we want to use 9 degrees of freedom. 9 degrees of freedom at 99% confidence gives us a critical t-value of 3.250. 3.250. So down here. And that's it for these critical t-values. Awesome. So let's do a couple more example problems where we look at conditions. Conditions to do a t interval, to create a confidence interval using the t distribution for means. So we got the safety specialist. Okay. They randomly selected 21 cars. So for these three conditions, the random, normal, independent, they met this first one. They randomly selected 21 cars. Different odd speeds in the sample were, all right, so this is an issue. The speeds in the sample were strongly skewed to the left. Remember, our sample data needs to be roughly symmetric with no outliers in order to meet this normal condition when the sample size is small. Since the sample size is less than 30, we needed this sample to be roughly symmetric, not skewed to the left. So we do not meet this condition. The last thing, individual observations can be considered independent. So since they did 21 cars on a busy stretch of road, I think it's a pretty reasonable assumption to say that there were more than 210 cars to choose from. And it looks like they agreed. The sample was probably less than 10% of the population. Reasonable assumption to make. Okay, we'll practice a few more of these. There are two different samples. Which sample satisfies the normal condition for constructing a t interval? Sample A, sample B, they both have 46 observations, which means they actually both pass that normal condition because the sample size is large enough. So both samples would satisfy the normal condition. This one ideally would be more symmetric at this point, like it's still skewed to the left. I'm not sure if they're actually estimating a mean. It's weird that it would do that, but oh well. They both satisfy the normal condition because their sample sizes are large enough. Had this sample size only been like 16 and it was still skewed to the left, then it wouldn't have passed. But again, since the sample size is greater than 30, the central limit theorem has been met. Do a couple more. So this person takes a random sample of 200 selling prices for that car, and more than 2,000 have been sold. So 200, it meets that 10% rule. 200 is 10% of 2,000, that's good. Again, it said that she took a random sample, that's good. And it's normal because that sample size was so large, and even the data are roughly symmetric. So looks like all the conditions have been met. You can absolutely create a confidence interval for this situation. All right, the last one. The sample sizes on each sample were less than 30. So the central limit theorem has not been met. Which one actually satisfies the normal condition though? Again, the sample data needs to be roughly symmetric without any outliers. So when we look at sample A, it looks like it's not gonna pass that condition because it's got these three outliers. These three data points that don't belong with the rest of the data. Sample B though is roughly symmetric. You can kind of draw a line right in the middle here and split up the data in half. And there don't appear to be any obvious outliers, like there wasn't a point way the heck out here or something. So I would say sample B is the only one that passes the normal condition in this case. All right, fantastic. That's the gist of what's going to be on your assignment for today. I'll get it posted in Schoology whenever it's back working. Otherwise, I'll see you in class sometime. Cool deal. Bye.